Jnanam Paramam Dheyam. Knowledge is supreme.
Last time I defined homological dimension of a module or an Noetherian ring, and we saw some basic properties. So, today I want to define a global dimension of a ring and relate it to the Krull dimension of the ring. And this will be very helpful for checking whether the regular ring is locally regular. Okay, so let us recall last time what I did was so our ring is fixed. A is Noetherian ring, and last time we saw homological dimension of a module over the ring. So this was the supremum. This is not the definition, but we deduce this supremum of n such that there exists a module n with x n a mn is 0 and non-zero. So also this was equivalent to remember checking that if you take a projective resolution of M, then the nth stage kernel is projective and after that it is 0. So this was the homological dimension and we saw some properties, and I will keep using the x. See, there are so many things here to check that it does not depend on the projective resolution of n. Also one can use the injective resolution of n and then tensor with m, home with m, and then compute the homologies or cohomologies. The results are the same. So here I am concentrating on you take the projective resolution of m and home it with n. Okay. So what is the global dimension? So global dimension usually denoted by GL dim A. This is by definition. You take supremum over M. M is an A module, and take the homological dimensions. This is the global dimension definition. We take this as a definition, and now we are going to concentrate on the local ring, and we will prove that when this is finite, that is equivalent to saying the ring is regular local, and in that case global dimension will be equal to the Krull dimension. So that is what the plan will be. It will take 2-3 couple of lectures. So we are going to assume now A is local, AM Noetherian local, ring, and we are going to relate these two integers GL dim A and Krull dimension of it. And because it is a local ring, we have a residue field, this A by M, and we will first show that the supremum you can only concentrate on this residue field as a module. So we will have much less calculation. So for that I am preparing now. So what we will prove is global dimension is finite if and only if the ring is regular. That is what the theorem we will prove. Alright, so now we are concentrating on the local ring. So let us recall quickly how do we translate modules being projective or free, how do you test? In general, we have to test that the home P dash this functor is exact. So, that one can be little bit improved. So, the proposition I want to note first time. We have now AM local. I will always assume the rings are Noetherian. Local contains part as a part a Noetherianness, and M is finitely generated A module. Then the following are equivalent. 1, M is free. 2, M is projective. 3, Tor J Mn is 0 for all A modules n and all j bigger equal to 1, and 4 Tor 1 M A by M is 0. So, note the advantage of proving such a proposition is fourth condition is involves only the module M and the residue field and only the Tor 1. So, we have very economical way of checking it here. Another thing is here also one if and only if 2 the projective modules are free over local ring. So, in general that was a big question whether projective modules are free or not. Okay, so let us quickly prove this. So, proof. So, first of all 1 implies 2 is trivial, every free module is projective. 2 implies 1, let us finish off. 2 implies 1. So, we have given the module is projective and we want to produce a basis. So, what you do is take a module M and now we are over a local ring. So, therefore, minimal number of generators for the module mu M, this is nothing but the vector space dimension of M by MM. This is precisely, this follows from Nakayama lemma. Or moreover, if you take any set of elements in M, if mod M it's a basis, then it already generates and it's a minimal set of generators. So, that is what I am going to do. I choose a minimal set of generators x1 to xn, is a minimal set of generators here. For M, and then write it as a quotient of a free module. So, now the free module is what do I denote F, this, where this is free of rank n and EI is going to Xi. Obviously, this map is surjective and we are going to prove the kernel is 0. If you prove kernel is 0, then this map will be an isomorphism, in particular M will be free, that is what one will be. Okay, so let us look at the kernel. So, we have such an exact sequence and I want to prove this kernel is 0. So, to prove kernel is 0, I will use Nakayama lemma. I have to use, so to show k is 0, it is enough to show k equal to mk. First of all, it is finitely generated because our ring is Noetherian. F is a free module finitely generated, therefore Noetherian, therefore submodules are finitely generated, so K is finitely generated. And if I prove K equal to Mk, then by Nakayama lemma K will be 0, and once K is 0, this will be an isomorphism and M will be free. Okay, so to show K equal to Mk, I am going to tensor this short exact sequence with the residue field. Okay, first of all, note that this module M is projective, therefore this short exact sequence splits. Once it splits, that means there is a splitting here. Splitting is a map this way, so that this composite is identity on M. So once it splits, then if I tensor, it will remain split, in particular it will remain exact. So therefore, I will get a sequence 0 K Mk to Fm Mf to M by Mm to 0. This is, we have obtained the sequence by tensoring over A the residue field, and it remained exact because the original sequence was split. But now this is a vector space of dimension n, this is also a vector space of dimension n, and this is a surjective map. And so finite dimensional vector space is surjective, is injective, is bijective. So this is isomorphism. Therefore the kernel is 0 here, that means Mk is 0. So that is K equal to Mk, and therefore K will be 0 by Nakayama lemma, and therefore we would have proved the fact that M is free. Okay, so that was to imply, so we have finished the proof of 1 if and only if 2. Now 2 implies 3. So remember, we have finished 1 if and only if 2, and I am proving 2 implies 3. So this we have done. Now this we are doing. Okay, so 2, what we have given is the module M is projective, and we want to check that the torr J's are 0. Alright, so if M is projective, then I will choose a resolution to be that itself. This is the first component is M and the remaining are 0. This is my projective resolution. And to compute torr, I have to take a projective resolution of M, tensor with N, and take the homologies. So I take this as a projective resolution and then tensor with N. So this is the identity map. When I tensor with M, and what do I have to do? I have to prove that torr J Mn is 0 for all n and for all j bigger equal to 1. But when I tensor it, the only complex, this is the 0th stage, and one stage etc. will come from here, but all of them are 0 because everything is 0 after that. So this is done, 2 implies 3 is done. Now 3 implies, now I will prove, okay, 3 implies 4 is trivial because 4 statement is only torr 1 and the module is A by M. So here, just to show you, this is just torr 1 and the module is a special module, the residue field, and 3 implies 4 is therefore trivial. So 3 implies 4, this is trivial. So this is trivial. So this is 1. Now we have to prove 4 implies 1. This is what we have to prove now. So 4 implies 1 we are proving. 4 says torr 1 M K is 0, and I want to prove the module is free. Alright. So this proof is similar to that what we proved 2 implies 1. You remember, we are assuming M is projective, we proved it is free. So it is similar to that. Okay. So, again start with, I have given 4, that means I have given torr mk is 0, torr 1 mk is 0. So, you take a resolution of m. So, it is f here and take k here, this is free and we are taking resolution of this, k is a module, k is the kernel of this is projective and therefore free, because we already proved 1 if and only 2, and now we want to do it torr 1. So, now when I tensor this sequence with the residue field, the long exact, what will I get? If I tensor this with a by m, I will get m by mm 0, f by mf and k by mk, and here the term will come torr 1 m, the residue field. This is a part of the first part of that long exact sequence, but and then so on, but this is 0, that is our hypothesis 4. When this is 0, this sequence is exact. This sequence is exact, and while choosing this the projective resolution, I would have chosen the minimal number of generators of m here, and this f is of rank n. So, therefore, these two will be isomorphic, and again the same proof as in the proof of 2 implies 1, m k by m k is 0 and therefore, k is 0 by Nakayama lemma. So, same as by then k is 0 by the same argument as in the proof of 2 implies 1. Okay, so we have to check some module is projective, we just have to check torr 1 mk is 0 or not. Okay, so that will also help us for a homological dimension. Now the so this proposition is computing homological dimension of the module over a local ring. So a local, now there is always our assumption, and M is finitely generated A module, then the following are equivalent. 1, homological dimension of M is less equal to n. 2, torr n or torr j m n is 0 for all n and for all j bigger equal to n plus 1. And third, torr 1 mk is 0. N or n plus 1, I am not sure, it will come out in the proof. I think n plus 1. So, proof. Okay. So, 1 implies 2. This is similar to the earlier proposition what we have proved. So, we have given homological dimension is less equal to n. That means, we have a projective resolution whose length is less equal to n. So, that means the projective resolution looks like this, m 0, then there is a p 0 and so on, and there is a p n and then 0 after that. This length is n, right. Now, when you tensor this with n, tensor this with n, then obviously only up to here the homologies will be, if at all, non-zero. This stage onward they will all be 0 because 0 tensor and etc. So, that proves 1 implies 2. So, 2 implies 3. This is trivial because I can take n equal to k and this is the j equal to n plus 1. So, n equal to k, k is the residue field and j equal to n plus 1. The real implication we need to prove is 3 implies 1. So, 3 implies 1. This we are going to prove it by induction on M. Proof by induction on N. N equal to 0, what we have given is TOR 1 and 3. That means we have given TOR 1 MK is 0, but by the earlier proposition, so TOR 1 MK is 0, this is given, and from here we want to conclude that homological dimension of M is less equal to N, that means homological dimension is 0, that means M is projective. But then by earlier proposition M is projective by earlier proposition. That precisely means that is homological dimension of M is 0. So, induction starts, actually it is free, projective and free are equivalent over local ring. Therefore, we are assuming now N is at least 1 and we resolve M, take a projective model which surjects on M and look at the kernel, that I call it M prime to 0, and remember that P is projective, this is projective. Now, when I apply TOR when I tensor this with K and take the long exact sequence, what will I get? I will get, there is a connecting homomorphism here from TOR n plus 1 MK, this is connecting homomorphism here, TOR n M prime K to TOR n PK. I am only writing that part only, then here it goes on TOR n MK and so on. This is the connecting homomorphism, this is the delta connecting homomorphism, this is exact we know. But then what is our assumption? By assumption this is 0, by assumption 3, we are assuming 3. So, this is 0 by that, therefore, and this is 0 because P is projective. This is the same earlier proposition, it is projective, therefore, TOR n is at least 1. After 1, TOR 1 and before that everybody is, after that everybody is 0. So, this is 0. So, therefore, this will be 0. So, this is 0. Now, apply induction hypothesis to conclude that, so that will imply by induction hypothesis homological dimension of M prime is less equal to N minus 1. And then apply one of the theorem we have proved, one of the lemma we have proved, that in such a situation homological dimension of M will be less equal to N. So, that implies homological dimension of m is less equal to n. So, that proves 3 implies 1 and it finishes the proof of the proposition.